All right. So welcome, gentlemen. Let me see. No major announcements. The only thing is, if you're trying to take advantage of the discounted access to Pearson, you can purchase the access code you have to purchase it from the Morehouse bookstore. So either go to the bookstore or call somebody there. You have to talk with somebody and just kind of explain everything. And it should cost like $100, and that should give you full access to My Math Lab for 2 years. Okay. And so what we're going to be doing today, we're going to continue with chapter 1. So today we will be working on section 1.5, transformation of functions. I think next week we'll be doing section 1.6, and that's going to be the end of chapter 1. And then the week after that, we'll be ready for exam 2, in other words, i.e. the midterm. We'll talk more about the midterm as we get closer. It's nothing really different. It's really just exam 2. Okay, so as usual, if you have questions, feel free to unmute yourself to get my attention or type in the chat. I do monitor the chat. And so with section 1.5, again, it's transformations of functions. A few objectives. 1, we'd like to define transformations of graphs. 2, use vertical or horizontal shifts to graph functions. 3, use reflections to graph functions. 4, use stretching or compressing to graph functions. Okay. So transformations. If a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f. Right? So last week we were working on section 1.4, where we were exploring a library of basic functions. We had a collection of functions. Let me check to see if I got some people coming in late. I do. Let them in. Okay. I had to get access. Let me see. Yeah, so that's fine. Yeah, you have to go by the bookstore. Once you get full access, you know how the late penalty works. But it's on that one assignment is small. As long as you kind of are prompt, like within the next couple of days, if you can gain full access and get started, 10% on a homework assignment is small, is nominal. You definitely want to just try to gain access as soon as you can, and just keep moving from that point.
Excuse me?
Yes.
I tried to log into Pearson last night, and it said I need a new access code. I couldn't do the work last night.
Yeah, so you had to purchase the full access. The discount is available in the bookstore. You have to talk to somebody in the bookstore.
The bookstore?
Morehouse bookstore.
Okay.
So my recommendation, if you can, is to actually just go up there and talk to like a clerk or like the manager or somebody and say, hey, we've been waiting for this like discounted access code, and we were instructed to come to the bookstore. Say something like that, and they should be aware of it, because we got an email last week that was like, okay, the deal was finalized or whatever, but to access it, you got to get it through the bookstore. And if you can't go in person, then I would try to call and talk to somebody. I don't know that it's available online, that discounted rate. So that's $100 for 2 years. That's actually a really good rate. Okay, so again, last time we were exploring a collection of basic functions. So then here we're going to be taking those basic functions and then manipulating them to generate graphs. Okay, and so that's what we're going to be doing, transformations. So let f of x be the absolute value of x, g of x be the absolute value of x plus 2, and h of x be the absolute value of x minus 3. Sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Okay. So here what we're going to do is make a table of values, choose several values of x, find the corresponding f, g, and h, and then plot these 3 graphs on the same coordinate plane. So let's start with, let me see, I'm going to make my table. So we're going to have our x, we're going to have our f of x, our g of x, and our h of x. We're going to let x be -3, -2, -1, 0, 1, 2, and 3. Can anybody describe the shape of absolute value of x? What does that basic shape look like? And the hint is it looks like a letter in the alphabet. Right. So this shape is going to be what? A V-shaped graph. And we're going to see how adding a positive on the outside of our basic function and subtracting a positive on the outside, how this affects the graph, right? So absolute value of x, all right, is just a positive distance a number is away from 0. So for instance, absolute value of -3 is just 3. Absolute value of -2 is 2. 1, 0, 1, 2, 3. Again, absolute value is the positive distance away from 0 that a number is. So then for g of x, we want to take those results from f and add 2 to all of those results. So then this is going to be what? 5, 4, 3, 2, 3, 4, 5. And then for h, we want to take the results from f and subtract 3 from all of those results. So we get 0, -1, -2, -3, -2, -1, 0. All right. So when we get ready to go graph, we're going to let G, we want to do G in green. And we want to do H of X in orange. Like this. Okay. Let me shrink this down just a little bit. Let's introduce some graph paper. Okay. All right. Oh no, what did I hit? Oh, way back. Okay. Why are you doing this? Come on. What? All right, there we go. Okay. So let's see. I think my origin. Style. Let's fill that with this color. It's still a little big. Okay. So I'll put my origin about like here looks decent. Actually, let's move it up a little bit. Okay. So our x values go from -3 to 3. So we can go about like here. Hopefully you all had a good weekend. Yeah. And then the y values, the lowest y value looks like it's -3 and the highest is like 5. Okay, so something like that. Again, actually we don't need that to go that far. We only need like 1, nope, under 1, 2, 3, 4 is more than enough. So I'm just going to move this over instead of, right? Smoothing here. 1, 2, 3, 4. Okay. And then the y values. Okay. 1, 2, 3. That's enough. 1, 2, 3, 4, 5, 6, 7 is fine. Okay, so to the right, this is our positive x direction. Up is our positive y. Here's our origin. This is going 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. These are negative, negative. Okay. Can I paste? Nice, okay. Style, green. Okay. Oh, well, we're not there yet. Okay. So now let's plot f of x. So the first point we have is -3, 3. And actually, let me change my paper. I'm a fan of this. Okay. So then -3, 3 is here. And then -2, 2 here. -1, 1. The origin is already plotted for us. And then 1, 1. Two, 2. Three, 3. Then what we're going to do is connect these using straight edges. So then we'll get something like this. Oop. Yep. Let's copy, paste. All right. So that's the graph of absolute value of x. Y equals absolute value of x, right? Come on. Okay, so then for G, let's do like this. And we'll get rid of what we don't need. And let's change this to green. Okay, and let's copy. All right, and so the vertex for G is at 2. So just it's right here, right? Okay, and then we'll go to graph orange. Let's go here. Oh, and fill this. Okay. So the vertex for this one is at -3. Okay. And then let me just change my paper to get rid of these lines. And so this is the graph of all three functions on the same coordinate plane. Okay. So absolute value of x is in black, right? That's f of x. Let's label this. X. This is our g of x. So you should notice something. How to, like, as far as the graph as we went from F to G, like what did we do from F to, what manipulation did we apply to F in order to produce G? What manipulation did we apply to F in order to produce H, right? So notice that G, we added a positive on the outside of our basic function. So that caused the original graph to go up by a factor of 2. With H, we subtracted a positive on the outside, and it caused it to go down, right? So that brings us, actually, let me check my attendance real quick. Okay, and let me check the chat real quick. It's okay. Okay, let's see. Okay, so this brings us to our first two transformations. So the thing with transformations, I feel like conceptually they're simple, but the challenge comes in that it can be information overload, right? So this brings us to our first two transformations. I think there are a total of like 10 different transformations that we're going through. So here, when we add a positive on the outside of our basic function, it causes a vertical change and it follows our intuition. So it shifted the graph up 2 units. When we subtracted a positive on the outside, that means it affected our y values. It went down that many number of units, right? Okay, so here's a type version of what we just experienced. And so again, so let C be some positive number. Then the graph of y equals f of x plus c is the graph of y equals f of x shifted c units up. And the graph of y equals f of x minus c is the graph of y equals f of x shifted c units down. Okay, so if we add a positive on the outside of our basic function, it shifts it up that many units. If we subtract a positive on the outside of our basic function, it shifts it down that many number of units. Okay. All right, so we saw what happens when we add or subtract the positive on the outside. It causes a vertical change and it followed our intuition. What happens? What do you think intuitively happens if we add or subtract a negative on the inside? How's that going to affect the graph? Is it going to follow our intuition or is it going to be something else, right? So let f of x be the squared function, y equals f of x equals x squared. G of x is going to be x minus 2 quantity squared, and h of x is going to be x plus 3 quantity squared. So then a table of values for f, g, and h is given on the next slide. The graphs of the three functions f, g, and h are shown in the following slide, and then describe how the graphs of g and h relate to the graph of f, right? So it's kind of a repeat of what we did before, but let's see what the difference is. So by now you should be comfortable with the basic shape of f of x equals x squared. You should be thinking like a U-shaped curve, a parabola. So now we want to see what happens when we subtract the positive on the inside and when we add a positive on the inside. So if outside manipulations cause a vertical change, then it stands to reason that inside manipulation should cause, let's see. So here we made the table. We chose these several values of x, found the corresponding f, g, and h, okay? And then if we plot these on the same plane, we get this image here. Where the blue is our original function, notice that with g, when we subtracted 2 on the inside, intuitively we might think, oh, well, there's a minus 2, so then we move it to the left by 2, but in reality it's the reverse, right? So subtracting 2 on the inside moved it to the right by 2. Adding 3 on the inside moved it to the left by 3, right? So inside manipulations cause a horizontal change, and they're typically the reverse of our intuition. Okay, let me say that one more time. Inside manipulations cause a horizontal change, and they're typically the reverse of our intuition. Okay. So let C be some positive number. The graph of y equals f of x minus c is the graph of y equals f of x shifted c units to the right. And the graph of f of x plus c is the graph of y equals f of x shifted c units to the left. So we subtract a positive on the inside, it moves to the right. We add a positive on the inside, it moves to the left. Horizontal change being the reverse of our intuition. Okay. So in this example, we're actually sketch the graph of this function. Can anybody describe to me the shape of, well, first of all, can you identify the basic function here? And then the second part of that question is, can you describe the basic shape, the general shape of the parent function? Going once, going twice, right? So the basic function here is going to be what? Y equals the square root of x, right? So square root function, the way I remember that image, the general image is is the top half of a sideways parabola. So if you think of a U-shaped curve or parabola, you turn it to the right by 90 degrees, so it's on the side, and then you cut it in half along the x-axis, and you keep the top half, discard the bottom half. That's the shape of the square root function. It's the top half of a sideways parabola. Okay, so we've identified our basic function. And then the recommendation is whenever we're doing multiple transformation in one function, we want to work our way from the inside to the out. So we want to start with the innermost nested manipulation. The innermost nested manipulation in this case is going to be the plus. So because we're doing this plus, we're adding 2 on the inside. That means we're going to have a horizontal change, and it should be the reverse of our intuition. Another way to get that manipulation correct, ask yourself what value of x makes the inside 0. All right, so since -2 makes the inside 0, that means we move it to the left 2 units. So one more time, inside manipulations cause a horizontal change, and they're typically the reverse of our intuition. Outside manipulations cause a vertical change, and they follow our intuition, right? So if we subtract 3 on the outside, that means we should go down by 3. Vertical change following our intuition, down 3 units. Okay. So here we showed our basic function and then the corresponding manipulations. So then we're going to start with the top half of a sideways parabola, move it left 2 units, and then down 3 units, and then that'll be our final graph. And we see it here. F of x is our original graph. When we added 2 on the inside, it moved it left 2 units. And then we subtract 3 on the outside, it moved it down 3 units. So I'm actually doing way better with you all than I did with my earlier group. I was like extra sleepy. I'm still sleepy, but I was able to get a little bit of a nap before I met with you all. But yeah, I made the mistake of eating some delicious spaghetti before meeting with those students. And so the itis hit me hard. I was like, with a hard H, a hard R, hard. I just wanted to go to sleep, but I was like, okay, well, we powered through and made it through. Let's see. Okay. So we've seen, I think, at least 4 transformations. 2 were outside, 2 were inside. Outside manipulations cause the vertical change, and they follow our intuition. Inside manipulations cause a horizontal change, and they're typically the reverse of our intuition. So let's see what happens here. So then here we have the graph of y equals negative f of x. This is going to be a reflection of the graph of y equals f of x in the x-axis. If a point x comma y is on the graph of y equals f of x, then the point x comma negative y is on the graph of y equals negative f of x, all right? So here what's going on, we're multiplying the outside by a negative. Outside manipulations cause a vertical change, and they follow our intuition. So if we multiply the outside by a negative, that's going to affect our y values. Our x values are going to stay the same, but our y values are going to go from positive y to negative y. So if the y values go from positive y to negative y, then our image is going to flip vertically over the x-axis. It's going to flip vertically over the x-axis. Again, whenever we have x comma y, the new graph is going to have the points x comma negative y. Notice the y is going from positive y to negative y. And here's an image kind of showcasing that. The blue is the original, the red is the new. We multiplied the outside by a negative. The x values, notice that the x values stay the same, but the y is going from positive to negative. So it flipped vertically over the x-axis. So then multiplying the outside by a negative causes it to flip vertically over the x-axis. What do you think happens when you multiply the inside by a negative, right? So the graph of y equals f of negative x is a reflection of the graph of y equals f of x in the y-axis. So in other words, we're flipping horizontally over the y-axis. If a point x comma y is on the graph of y equals f of x, then the point negative x comma y is on the graph of y equals f of negative x. right? So when we multiply the inside by a negative, the y values stay the same, but the x values go from positive x to negative x, right? And that's what we see here. Notice that the y value stayed as is, but the x values went from positive to negative. So it caused our image to flip horizontally over the y-axis. Okay, so I think at this point we have a total of 6 of our transformations. You know, adding on the outside with 2 vertical, adding and subtracting on the inside were our horizontal shifts, and then multiplying on the inside or outside cause reflections. So explain how this graph can be obtained from the basic function absolute value of x, right? Okay. So if we start with y equals the absolute value of x. So now again, when we're doing multiple transformations in one equation, we want to work our way from the inside to the out. So the innermost nested transformation is going to be the -2. So if we subtract 2 on the inside, that means it should be a horizontal change, and it should be the reverse of our intuition. So that should go 2 units to the right in the positive x direction. So we start with a v, we go right by 2 units. Now working our way out, the next manipulation is we multiply the outside of our basic function by a negative. So outside manipulations cause a vertical change, multiplying by a negative cause a flip. So it should flip vertically over the x-axis. So we're going to say flip over the x-axis. And then lastly, we added 3 on the outside. So that means we should shift vertically up by 3 units. So we should move it up by 3 units. We started with a V-shaped graph with the vertexes at the origin. Notice we went right by 2. We flipped it vertically over the x-axis, and then we went up by 3, and that was our final graph. Okay. So, okay. So in this example, we're given these f, g, and h. We're asked to sketch the graphs of f, g, and h on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. F is what absolute value, so we've done this one. Absolute value of -2 is 2, and then 1, 0, 1, and 2. Okay. We'll do g in green. So we want to take those results and multiply them by 2. So this becomes 4, 2, 0, 2, 4. And then for h, we want to take the results from f and cut them in half. So we get a 1, 1/2, 0, 1/2, and 1. If we plot all 3 of these on the same coordinate plane, okay. So our original is f. Notice here, we multiplied the outside by a number larger than 1. Multiplying the outside of our basic function by a number larger than 1, outside manipulations cause a vertical change and follow our intuition. So this got bigger vertically, follows our intuition. So we call that a vertical stretch. Like, I don't know if you all are familiar with like this candy called like Laffy Taffy. I don't know if they still make that or not. But like with taffy, it's like, you know, kind of gooey a little bit. But if we were to imagine that the V was drawn on some taffy and we stretch it vertically, that's essentially, it gets tall and skinny. It gets larger in a vertical sense. So multiplying the outside of our basic function by a number larger than 1 causes a vertical stretch by a factor of 2 in this case. Multiplying the outside of our expression by a number between 0 and 1 is going to get smaller vertical. It's going to get smushed vertically. So we call that a vertical compression by a factor of 1/2. Okay. All right, and I think we have 2 more. Okay, so the graph of y equals a times f of x is obtained from the graph of y equals f of x by multiplying the y coordinate of each point by A and leaving the x-coordinate unchanged. The result is going to be a vertical stretch away from the x-axis if that A is larger than 1, and it's a vertical compression towards the x-axis if that A is between 0. Right? So we're multiplying the outside by these different numbers. If A is negative, first you graph the absolute value of A times f of x by stretching or compressing, and then reflect it vertically over the x-axis. Right? Because we multiply the outside by a negative, it flips vertically. Okay. So then here, now we're going to be multiplying the inside of our basic function by different numbers. So the graph of y equals f of b times x is obtained from the graph of y equals f of x by multiplying the x coordinate of each point on the graph by 1 over b and leaving the y coordinate unchanged, right? So like before, remember we said inside manipulations cause a horizontal change and they're the reverse of our intuition. So when we were doing the rigid transformations where we were just changing the position, whenever we did the inside manipulation, before we were asking ourselves, okay, what value of x makes the inside 0? So now we're doing like, well, what value of x makes the inside 1? If we multiply the inside by a number larger than 1, then intuitively you might say, oh, well, it should get larger in the horizontal direction, but in reality, it does the reverse. It's gonna cause a horizontal compression by a factor of 1 over b, right? Whatever that b is, right? So again, if we multiply the inside by b, we're going to get a horizontal stretch away from the y-axis if b is between 0 and 1. Notice this is a small number, it gets bigger horizontally. We get a horizontal compression towards the y-axis if b is larger than 1. So we're multiplying the inside by a number larger than 1, it actually gets smaller horizontally. It's the reverse of our intuition. If b is negative, first graph the absolute value of b times x by stretching or compressing horizontally, and then we flip horizontally over the y-axis. Right? Okay. And I think that might be all 10 of our transformations. We had two for vertical shifts up and down, 2 for horizontal shifts side to side, 2 reflections, either flipping vertically or flipping horizontally, 2 for stretching and compressing vertically, and then 2 for stretching and compressing horizontally. And that's a total of 10 different transformations, right? Okay. So use the graph of this function in the figure whose equation is not given. Sketch each of the following graphs, right? So I'm just going to stop where I stopped with my students earlier. We still have a couple more examples. For part A, we multiplied the inside by a number between 0 and 1. For B, we multiplied the inside by a number larger than 1. And then for C, we multiplied by -2, right? So for A, if we multiply the inside by a number between 0 and 1, that should cause a horizontal stretch by a factor of 2. So it should get wider horizontally where the y values stay the same, but the x values are doubled. So stretch horizontally by a factor of 2. Okay. And then for B, if we multiply the inside by a number larger than 1, we're multiplying the inside by 2. So that's going to cause a horizontal change, and it's going to be the reverse of our intuition. So it should be a horizontal compression by a factor of 1/2. Horizontal compression by a factor of 1/2. So in other words, our y values stay the same, but the x values are cut in half. So that way the image moves towards the y-axis. And then lastly, when we multiply the inside by -2, it's going to be the same image, but we're going to flip it horizontally over the y-axis, and we see it here. Okay. Let's zoom one more time. Okay, I think we're okay there. Okay, so here, right, if we want to use transformations, first identify the parent function or the basic function. Basic function here is y equals x squared. Okay. As we go to identify our transformations, the recommendation is to work your way from the inside to the out. So the innermost nested transformation is going to be that -1. We subtracted 1 on the inside, so that should move it to the right by 1 unit. So we should go right by 1 unit. Next, we multiplied the outside by 2. So that should cause a vertical stretch by a factor of 2. Next, we multiplied the outside by a -1. So that's going to cause it to flip vertically over the x-axis. So we're going to say flip over x-axis. And then we added 3 on the outside. So we want to move it up 3 units. Okay. So here you can see we started with a U-shaped curve. We went to the right by 1. Then we flipped over the x-axis. We went right by 1. We vertically stretched by a factor of 2. We flipped it over the x-axis, and then we went up by 3. And that's our final graph. Okay. And I think that's where we stopped with my students earlier. So we're going to stop in the same place. Are there any burning questions before we go our separate ways? Going once, going twice. Let me make a copy of this available. Come on. So when this bar finishes loading, you should receive a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. And I'll see you Wednesday, same time, same place. Okay, take care. Peace.
Professor C, I have a question.
Yes.
So it says my trial ran out on Pearson for the math. So should I just buy the access, I would guess you'd call it, or what should I do?
The discount, to get the discount, you have to contact the Morehouse bookstore. So my recommendation is just to go to the bookstore if you can, kind of explain everything. And the discount should be for $100, you can get full access to My Math Lab for 2 years.
Okay. 2 weeks? Years. Okay. Thank you.
All right, gentlemen, I'll see you next time. Take care.